Well, hi there. Happy Monday to you. Welcome back. And we are going to keep talking about this most beautiful calculus symbol, the definite integral, and how elegant it is and how it accomplishes what we want to do in just a really lovely way. So we'll talk about how integrals exist for continuous functions. We've already talked a little bit about the terminology of Riemann sums, how Riemann just means rectangles, and specifically infinitely many rectangles where they are summed up using that Greek symbol. And then how the integral is the exact representation of area. All right, so let's look again at this integral developed by Leibniz, coming off of Riemann's work. So, of course, we have the integral sign right here. We have the lower limit and the upper limit from a to b, which limit us on our x-axis. It's read like this out loud: the integral of f from a to b. The function itself is what we call the integrand. Dx is the variable of integration. It also helps you determine the axis that you're working on. And when you find the value, it represents exact area. So the result of an integral is the value of the exact area. Under the curve, or maybe we could say between, let's say that's better, between the curve and the axis. Okay, we're not just estimating anymore. We're not just, oh, this method is better than that method. We're now getting the exact value. Every continuous function has an integral. It's integrable is what we say. Okay, that's the modifier for that. So if the function is continuous, it can have corners, it can have cusps, it just can't be broken with asymptotes or any other discontinuity, then we can find its integral and its exact value. So if f is non-negative, that means it's above the x-axis, and it's integrable, that means it's continuous over the closed interval, then the area under the curve, y equals f of x from a to b, is defined as this integral, and you will have positive area. So if the function is positive, it's not negative, so it's above the x-axis, then you'll have positive area. The area is negative when the function is negative. So if a section of the function is negative, then the area there on that section would be negative. So I was kind of setting you up for this on the worksheet, because I did ask you how area could go down, how it could be smaller, how you could have a bunch of positive area and then all of a sudden the area would go down. And I was trying to get you to look at the graph and to notice that the graph dipped below the x-axis. And when it does that, then the area in that section is negative, which would pull the overall value down. So let's look at a section above and a section below. So the blue rectangle is an entirely positive graph, and so its yielded area would be completely positive, whereas the sort of tan rectangle, light brown rectangle, is below the x-axis, and its yielded area would be entirely negative. Now, we don't need geometry to do these questions. Excuse me, we don't need calculus to do these questions. These are straight geometry. These are perfect rectangles. So if the shape is geometric in nature, you don't need calculus. You only need calculus when you start having curves. All right, so remember, the Greeks could do all the geometry. That was their bread and butter. Okay, they could do all the geometry. It was not until and they could estimate the curves. It was not until we got Newton and Leibniz during the Age of Enlightenment, during the Renaissance, where we could then finally tackle the exact area of a curve. So what does this symbol mean? Okay, if I asked you for the answer for this. So usually it helps to draw this. Okay, this is a constant number 7. And so that means the area bounded by the constant value 7. Okay, there's the function for 7, starting at A and ending at B. Now, does it matter where the A and the B are? Do they have to be on the same side of the x-axis? Well, let's check it out. Let's say that A was negative and B was positive. All right, that would form the area bounded between the curve and the x-axis. Okay, well, I need to know the width of this function. So you always take the larger number, which is clearly B, and you subtract the smaller number, which is A. So we have B minus A as our length. It's irrelevant what A is. It doesn't matter if A is positive or negative, you're still going to subtract it. And then we need the height, which is constant at 7. And so the value of this would be the base times the height, or B minus A times 7, or 7B minus 7A. All right, what about this one? How would we evaluate that? Okay, again, I really feel like it's helpful to draw my understanding of what this is. All right, so let me get my axis on here. And I'm going now with something that is 7x. Now 7x is a very steeply sloped linear equation. So 7x is up 7 over 1. So there's y equals 7x. And we're going from A to B, but we are told in this one that A is greater than 0 and B is even greater than that. So they're both on the same side of the x-axis. So we can put A here, we can put B here. Okay, this gives me a perfect trapezoid. And so the value of this integral would be just using the trapezoid, 1/2 times the base and times the average of the heights. So 1/2. The base this time is still B minus A. Now the height. How tall are these? Well, A is the x value. And if I plug A into the function, I will get the y value. And so the y value is 7a. If I plug a into the f of x curve. And the other height is up here. That's the height 7b. So my height is 7a plus 7b. So I can simplify that. How about I pull the 7 out? So I have 7/2 times b minus a times a plus b. And if I FOIL that together, I'm going to get b squared minus a squared. So that's the expression for the exact area underneath that curve and above the x-axis. All right, how about now if we specify from -2 to 5 of 7 theta. So this is the theta axis this time. 7 theta still looks like 7x did. And we are going from -2 to +5. All right, so the height up here at +5 is 35. And the slope, oops, down here, that's going to give me a value of -14. So I want the area formed by the triangle here, and so now one of the triangles is positive and the other triangle is negative. So my negative triangle here would have negative 1/2 base times height. So 2 times, well, the negative would be coming when I had my 14, negative 14. All right, so that works out to actually be negative 14. And my positive area would be 1/2. The base is 5, and the height is 35. So we're looking at 175 over 2. So the total area here will come down negative 14 plus 175 over 2. So make sure you keep the negative. So the answer was going to be less than 175 over 2. So we're looking at 73.5 is the total amount of area for that section. Okay, now the square root function might freak you out a little bit when you look at it, but you just have to take a step back and realize what that is. Okay, now the title says it's recognizable. So, okay, is it really recognizable? Let's check. Y equals the square root of 4 minus x squared. You might not recognize that until you square both sides. So if I use parentheses to square both sides, now I'll have y squared equals 4 minus x squared. You still might not quite recognize it until I add x squared to both sides. X squared plus y squared equals 4. And then maybe, oh, right, this is a circle of radius 2. More specifically, it's the top half of a circle. If I wanted the whole circle, there would be a plus and a minus here, but I'm only specifying right now the top half of the circle, the semicircle, so it's above the x-axis. So let's take a visual of this. And so we are looking at a nice semicircle of radius 2. Now I want the area beneath that curve, between that curve and the x-axis, but I want my bounds on 0 to 2. And so the area I'm looking at is only in the first quadrant because I'm limited from 0 to 2. So I'm really only looking at a quarter of a circle. And so I want 1/4 pi r squared. Since the radius is 2, then the answer to this value is pi. The answer to this integral is the exact value of pi, only because I knew the geometry of this. We're still thinking like the Greeks. They could do the geometry because it was a recognizable curve. Even though there's a 2 here, this is still a recognizable curve. All the 2 does is shift the semicircle up 2 units. So now my semicircle is moved up, and my semicircle now looks like this. And the semicircle itself is sitting on top of a rectangle. Okay, I think I got everything labeled here. So I'm going to have a full semicircle this time, because notice the bounds go from -2 to 2, so it's the entire semicircle on top of a perfect rectangle. So we're going to have the addition of 2 geometric shapes here. So we're going to have 1/2 pi r squared, that's half of a circle, plus base times height for the rectangle. So 1/2 pi times the radius of 2 squared times the base of the rectangle, which is 4, and the height, which is 2. So that's 2 pi plus 8. All right, here is another semicircle, but this time I want you to notice it's the negative. So it's been moved up 2, but it's the bottom half of the semicircle. So what will that look like geometrically? All right, here are my ends, but this time I want the lower half of the semicircle. So it's this one. And I want the area between that and the x-axis. So I'm looking at from -2 to 2. I'm looking at this area under here. Now that's not so much a geometric shape, but this is in green. And the outline of the two together make a rectangle. So I'm going to subtract 2 geometric shapes to get the non-geometric shape of yellow. So I am going to start with the base times the height, that's the 2 pieces put together, and I'm going to subtract the semicircle. So the base is 4 and the height is 2, and I'm going to subtract the semicircle with radius 2. So this one would give me 8 minus 2 pi. 8 minus 2 pi represents the yellow part that's left, which is what I was looking for. All right, our last couple of functions are going to be trig functions. And I'm giving you a value. So I'm starting with this. I'm telling you that from 0 to pi, underneath the sine curve and above the x-axis has an area value of 2. And so here's your sine curve. And we know that 0 to pi goes here. So what I'm telling you is that this arch has an area value of 2 cubic units. Excuse me, 2 square units. So then my question is, what's the area if you keep going and you go to 2 pi? Well, you can use the symmetry of trigonometry. Right, we know that this area up to pi is a value of 2. And if we keep going to 2 pi, that this area has the same shape. But because it's below the x-axis, it's negative. And so the combination of those two together, the positive area and the negative area, give me an answer of 0. There is no cumulative area accumulated from 0 to 2 pi. What happens if we look at cos? All right, cosine of x minus pi halves. So these are just things, that I expect that you know the shape of cosine. All right, so there's our cosine. We know that cosine crosses at pi halves. But this cosine is moved right pi halves. So the graph that I've drawn here needs to be moved over to the right pi halves. So the maximum is happening above pi halves. All right, so let me erase the original. So we've got the original one pretty much gone. And so my question now, well, the bounds of this are from 0 to pi, so we need to draw what's missing here. And now go from 0 to pi. Well, this has the exact same shape as the sine graph did. And so that value of 2 means that this value is also 2. Okay, what if I take this cosine graph and I don't move it to the right, but I shift it up 1, and I go from 0 to 3 pi over 2? All right, well, let's take a look at that. All right, here is 0, pi halves, 3 pi halves. Okay, pi is right here in the center. So what if I move this shape up 1? All right, well, if I do that, it's going to come down and hit at pi and then be up here. And what if I want to know from 0 to 3 pi over 2? So I'm going to have to put some pieces together and use some addition and some subtraction to figure this out. All right, now let's subdivide this a little bit. Okay, that's going to give me an exact rectangle. Didn't quite draw that very well, but underneath from 0 to pi over 2. And I need to go over to here. Wow. Let me try and make this look a little better. It's a little bit better. Okay, so I want all of this area, and I want all of this area, and all of this, and the rectangle here. So how can I piece this all together? Well, if you think about the area in here, that's the area of 2 again. So the green area is 2. How can I get the yellow area? Okay, and then like what about this area here? All right, well, let's start there. All right, well, that's half of a shape that would look like this. And that shape in its full form with both sides is 2. So this side must only be 1. So we've got 1 there. And then what about the rectangle it's sitting on top of? If we label my y-axis, I'm going from 1 to 2. All right, so then that is a rectangle where base is pi over 2 and the height is 1. So that area is pi over 2. Okay, that represents this rectangle here. Okay, now let's deal with the space between pi halves and 3 pi halves. Look at the yellow and the green together. The yellow and the green together form another complete rectangle. The base of that rectangle from end to end is pi. That's going from 3 pi halves to pi halves. The height of that rectangle is 1. And so the area altogether of that would be pi. Now I want to take away the green area to be left with just the yellow area. So altogether we've got 1 plus pi halves plus the rectangle pi, but subtract the green value of 2. And so all together, we end up with 3 halves pi minus 1. Represents the value of the yellow area altogether. So we're just putting together all the pieces. Okay, so you got to think like a geometer, a geometrician, okay, and be looking for areas that you recognize, whether they are trapezoids or rectangles or triangles or semicircles or pieces of trig graphs that can help you find the exact value. Okay, and then we'll come back and we'll review both this, and I also want to actually talk about the worksheet. Maybe I'll do that right now. So I'm going to pause this a minute and pull up your worksheet, the annotated version that, that I put in Canvas for you, okay? Okay, so hopefully you've pulled up your annotated worksheet. A couple of you forgot to draw your rectangles when I asked you to make a sketch. When I asked you to make a sketch illustrating RAM, there's got to be rectangles on there, 4 of them going from right to left. Pretty much everybody got that right as 14. The over or under estimate, a RAM reason must only be based on increasing or decreasing. So you got to tell me if it's an increasing function, it means this. If it's a decreasing function, it means this. It doesn't have anything to do with concavity. Some of you got confused on that. That would be for a trap question. Trap question has to reference concavity, but a RAM reason is based on whether the majority of the interval is increasing or decreasing. All right, and number 2, most of you did fine on the calculator parts except for here. Okay, and I was trying to get at the fact that even though the region started out as 4, that has a length of 4. Then when I had you switch to a base of 5, so an interval of 5, the overall value of your integral went down. So how does going farther along on your x-axis mean that you're going down? And this is where I wanted you to look at the graph and notice that as soon as you got beyond the value of 2, it started to go below the x-axis. And area, those rectangles formed, or those paraboloids formed under the x-axis, are now accumulating negative area, which serve to pull your overall answer down. So I wanted you to look at that. Your shaded region trap was really, really good. Make sure you always have units, and especially in an application problem. So if I'm asking you about finding the volume, then make sure you have the corresponding units to go with that. Okay, but overall, really, really good worksheet. So good work for the last week. Okay, I'll see you on Tuesday morning. Hope you guys have a good start to your Monday.